All right, so now in this lecture we are going to look at how we can apply our understanding in finding a definite integral into finding the area between curves here. So as I just now said, this is actually an application, and it's one among the infinitely many applications out there of definite integral. Now, but this application we're about to do here is going to be the most direct one, the most direct application of a definite integral. And so what do I mean by the most direct application of the definite integral? Now, the idea of using definite integral for finding area is not new. Back in some of the earlier lectures that I have made when I was explaining what an integral is, what a definite integral is, I already brought in as examples that my students have seen earlier, that we can apply the integral as a tool to find the area that's happened between a given curve f of x. So now you have a curve of a function f of x, and then between that curve and between the x-axis, there's a space there between that, and then we're gonna restrict that curve inside an interval from a to b on the x-axis. There we produce for ourselves an area. And so we already learned how we used the integral, the definite integral, as a very effective tool and the best tool to find the exact, I'm talking about the exact area inside between the curve and the x-axis and inside of that interval on the x-axis here. Okay, so we have done that before. So in this particular lecture, the connection here is that this is actually, in this video lecture, I am going to extend that idea about how we apply, in general, how we apply a definite integral into finding an area, and then between curves. So what does that mean by area between curves? I mean, you have learned already at this point in algebra, in calculus, that any function or even any equation has a curve. It's just basically the graph. And so you have a curve, then you have a curve, then you have a curve. Doesn't matter if it has to be straight line or bent curve or whatsoever, and then you have a curve. And so now area between curves, see, there's a curve, there's a curve, there's a curve, there's a curve. So we want to use an integral, the definite integral. We want to use the definite integral to find the area of a region that's trapped inside or trapped between curves like that. And that's the idea. And so finding area is the main problem, but alongside with that, we have to always apply the definite integral, and then we will explore how important the definite integral can become as a tool for us to find us any of these area. Now, I have to also emphasize, we're talking about the exact area of these irregular shapes here. It's not a rectangle, it's not a circle, it's not a triangle, it's not any of those regular shapes that we have, that we have seen. So it's just an irregular shape in general, a region that we're gonna be able to find the exact area. Okay, and so now let me put away just some of the shading here. Okay, so before the journey gets far, I have always mentioned this right after I introduced the definite integral, and at the end of the lesson about what the definite integral was. A definite integral is accumulation. I keep emphasizing this, and here throughout the entire application and many other applications, anytime you will see me giving a lesson on the application of a definite integral, I will constantly remind anyone this at the beginning of the application example. A definite integral is accumulation. Any definite integral is accumulation. So a definite integral is accumulation. A definite integral is accumulation. Okay, and so what do I mean by that? What do I mean by just keep emphasizing that? And how will that help into this picture over here? We will explore all that. So here's the thing. So now to get started, imagine that at some point, or you must have seen this some point in your life, but you probably never realized that. And so now let me point this out. Imagine that if you're looking at a child in a class like, say, you know, first grade, second grade, or pre-K, or, you know, kindergarten, whatsoever, but when the teacher is telling the children that, hey children, hey kids, let's color this shape right here. Let's color a shape. So this is what any child would do right here. This is what any child will do. They use their color pencil and start doing this. That's how they're coloring it. All right. Some other child in a shape, some other child is doing this, okay, to color. And then, of course, I wish I have some color pencil here, but that's the idea right here. So now what we see here with us, the much more mature people and having math background, and this is the way how I see it, the action, the work that any child is doing in terms of coloring the regions here, or the coloring the shape here, the child is actually accumulating. And the more accumulation, because you see all of these stripes that the child is making with color pencil, the child is making, and it's just, and indeed that is the way how any teacher is showing a child to make color, to do coloring of a shape right there. Okay. And so these are all the stripes right here that start. And so now what we realize here with some math is we're actually accumulating, because the more, see, we don't just color back and forth at only one instant. But the point is, as we keep doing more from the left to the right or from the bottom up, like here, we get more color. Our color becomes thicker and thicker, and eventually it covers the whole region. Okay, and so that's the accumulation idea that I was talking about right here. So we got stripes. Fundamentally, the idea now we got infinitely many stripes, and we're accumulating those stripes right there from definitely, now you can see that in the picture. We have to have a starting point, and then somewhere at some point we end that accumulation, and that's where we already had the complete shaded area. Okay, and now for us here, the children who are coloring the picture, they never realize that they can also find an area, the exact area of some irregular shape like that. But, you know, for us now, we can even find the area. We can know how much area we color. Okay? And so now allow me to get on the other board. I'm going to erase the picture here. And let's look at some deeper understanding right here. All right, so now, as I have pointed out, coloring, or now when we are getting area right here, then we're accumulating stripes. So let's think about the stripe, and right here in this scenario, I put the stripe vertical, meaning it stands vertically up from where the x-axis is. And we'll get to that later. But now, any stripe. Some child use a broad tip color pencil. Some child use a thin tip color pencil. Okay? But in the end, any stripe, the camera might be far, and then any of you sitting from far looking at this, you probably don't see much, but any stripe here has a thickness. Okay? So even when I'm attempting to draw the curly braces to include all of that thickness here, the curly brace here itself is already a lot bigger than the actual thickness of that. But in the end, the bottom line now is that any stripe that we draw has a thickness. Even each of my pencil tip that I'm making here in the writing has a thickness. Okay? And then the stripe that we're drawing here has a height, a length, has a length. As a matter of fact, I should have started out with using that fundamental term. Any stripe here has a length. So this is the length of the stripe. Okay? And so here, think about it this way. Again, back to the story of the child making color. You see, if the child is doing this, making those stripes all the way through, this is probably at the very beginning child, like preschool or something like that. The teacher is going to come around and say, hey kid, you're overcoloring, right? It's not, you're shading outside, okay? And then as the child grow older, he or she is gonna realize that for each stripe right there, for each stripe that the child is doing, they only need to make the stripe to be somewhere between the curves, between these curves that define the shape right here, and that's between the curves, okay? But now what I'm really trying to emphasize now, see, so inside between the curves here, any stripe that we're drawing has to have just a length. See, we cannot just overdraw the stripe like that, right? Because if we don't restrict that, into a certain length right here, then we don't know where to stop. You see what I'm saying? Okay, and so in that way, now that enforces our understanding that any stripe has a length. So the length is to be defined by, the length is restricted by where we are between the curves. And that's the whole idea here. We're looking at between the curves like that. Okay? And so now we have the length of any stripe and we have the thickness. So that's one fundamental over here. Anytime we're multiplying the length, okay, or in some case we can refer to that as a height. We'll get to that later, okay? But anytime we're multiplying length with the thickness, it's a multiplication there. Okay, length times thickness, or height times thickness. That's the area of one stripe. So surprisingly, this very thin, just made by a pencil tip, usually we think that there's no need for an area, but there is an area, okay, where the thickness is infinitesimally small, but there's still a thickness, and then that thickness multiplied with the length of your stripe, we get the area of one stripe, okay? And now observe closer the action of what the child is doing in terms of coloring. See, the child, as I explained earlier, any child is naturally smart enough, see, to know that, hey, let's not just up and down only at one spot. We have to go further, make more stripes, because as we progress from the start to the end right here, then we're gonna cover up the whole region here. Eventually, that becomes the shading, okay, of the color. The shading of the whole shape right here. And so in that way, that's where I see it's accumulation. Any stripe has an area, so now we're accumulating. An integral is accumulation. A definite integral is accumulation. Okay, we're accumulating all of these stripes, and that's how we get the total area. Okay, that's how we get the total coloring of that shading right there. All right, and so now, and even for any child that coloring, there has to be a starting point. We don't start coloring from out here. And like I said, if the child start coloring from out here, the teacher is gonna come around and say, "Hey child, hey kid, you overcolored, right? You made too much. You're supposed to get it inside of that area only." And the kid is like, "Oh, all right." So in that way, what do I mean? But what can we observe from that? The idea now is that any accumulation that we're doing here has a, okay, so let me call, has a start, okay, to an end. Now I purposely draw the straight vertical line right here, but the curve itself doesn't have to be the straight, but the point now is that the shading that happens here, there has to be an ultimate start and an ultimate ending. Okay? And so in that way, now it's accumulation, and it happened from some starts to an end like that. And this is giving us the total area. Okay? All right, so at this point you probably realize, and now I have to admit, I would like to show maybe my students, I would like to deliver to my students, my public viewers, this fundamental understanding rather than just rush directly into a formula, because I want you to get that fundamental understanding, and then you should be able to create your own formula out of that, okay? Because so the way I'm approaching this particular material, the way I'm teaching this material is a little unique and quite different from the way how many other calculus textbooks, standard calculus textbooks are given. I mean, usually textbooks just get straight into the formula. Hey, if you're doing this, you get that formula. If you're doing that, you get that formula. But here I want you to understand ultimately to find any area. That's the concept. We take infinitely many stripes. We're accumulating infinitely many stripes, where each stripe here has an area obtained by the length times the thickness. And then we're accumulating. That's what the integral is for. We're accumulating from a start to an end. That's what I want to emphasize for anyone. Okay? But now, there are a lot more about this. So let's look. Okay, so now just right here in this picture that I have already made already, a region is just a region. Okay, a region, a shape. I mean, for a child, when he or she is still developing, and the child didn't need to know about the x-axis and the y-axis up until what, maybe the 6th grade or 7th grade, they start knowing about the x-axis and the y-axis. But for a child younger than that, a region is just a region. A shape is just a shape. A triangle is just a triangle. Okay? See, so now we're more mature in that. So this is what we do. We put x and y axes. Okay, so now let me erase some of these extra drawing to blend in my axes right here. All right, so now for us, we're a lot more mature, so we put x and y axis here. Okay, and so now here's the thing. I mentioned that this also earlier, but I now have to emphasize. Some child chose to go with stripes like this, that when we're drawing it, you can sense that it's vertical. And like I made in a different picture earlier, some child can shade like this. Okay? And so now in reference with the x and y axis that now I just put on the picture over here, there's the x axis and there's the y axis. And let's stay right here with this picture I already had. And then we will get to this other style later. But now think about, put yourself in that scenario that once you have already chosen. So how you go with your stripe, it's your choice right here. Okay, so here I have already chosen to use vertical stripe. Vertical stripe means, see, it stands vertical, it stands perpendicular with the x-axis, and it's parallel with the y-axis. Okay, so in case that we're accumulating these vertical stripes, just like some child decided to use vertical stripe to color out the whole region here, then think about it. Each vertical stripe right here, okay, and so now if we draw that all the way to hit with the x-axis, then isn't the thickness has to be measured in terms of the change, the infinitesimally small change, okay, and it's so far away and so small so that even from a very far away and even right from the camera to here, you won't even tell the difference. But that is the differential dx, because we're on the x-axis. The thickness here, with us having some mathematical understanding, a thickness is now quantified as the difference between some two x values on the x-axis. And then when the thickness becomes so small, infinitesimally small, then it becomes a differential dx. Okay, so now I'm talking specifically about in this case right here where I already have used vertical stripes. So it's consequently led to this same formula, this same fundamental, this only formula ever. That's the way how I see it. This is the only one formula ever. Thickness now becomes dx. Let's make that connection right there. Thickness becomes dx. And then the length or the height. You see, so it makes sense this way, that just like how I explained earlier. So now the stripe is here, okay? And if the child is shading with the stripe that goes cross through the whole region, the teacher is going to be is going to come around and say, hey child, you need to correct that. You need to put your stripes inside the shape. And so inside the shape right here, now a little further, a little deeper looking into that, then it means, you see, we have to restrict the length of the stripes between the curves. All right, between the curves. But now having even a closer look, now the curve here, this case, because it's just the way that we place the stripe vertical. We place the stripe vertical, so it has to be between, so the height of this stripe here, or the length of this stripe here, has to be between some upper curve and some lower curve. It's the way it is. You cannot find the length of the stripe here from the difference between the right curve and the left curve, which is impossible, right? So this vertical stripe that we used, and like I said, use a vertical stripe, using vertical stripe or horizontal stripe is our choice. So right now, let's stay with the vertical stripe that I already had in the picture here. Okay, so now the length here, or we call it the height, is just the difference, right, between upper curve minus the lower curve right there. Okay, and so now on my other board, that's length or the height. Yes, this is upper curve. Subtract the lower curve, because we express curves, we express functions as curves. Okay, and so now even further understanding. Upper curve and lower curve, yes, that's just the physical look of the curve. Upper curve or lower curve? Upper curve or lower curve? But in the end, as I already mentioned so many times, that in math we use curve as a way to represent a function. And a function has a main independent variable. And so I also had an explanation in a different video lecture about how important this dx differential is in connection with a definite integral or any integral. The bottom line we need to keep in mind here is that once we have chosen the dx right here, see from the earlier lecture I've been explaining that the dx here, or the d expression here, has to always be consistent with the variable, the main variable used in any of these functions. Okay, so what do I mean by that? So if this d expression here is a dx, that means the upper curve and the lower curve, these all have to be functions of x. So some function f of x to be the upper one, and some lower function, some function g of x, have to be the lower curve. That's what I meant right here. The dx expression has to be consistent. And so now we chose the dx expression. And so that means we have to express our curve. We have to be able to express our upper curve and lower curves as some two functions in terms of x. That's what my point is. Okay, and then we take the difference between upper curve and lower curve as functions of x. Then that difference there gives us the length of our stripe. All right, so now in the picture, see, so the length of our stripe at this instance is going to be, if this is some f of x and this lower curve is some g of x, then between these two curves that defines the length. And so the length is right at that instance where we take that difference between f of x minus g of x, and right at that instance x. Okay, all right, and so now it's accumulation. An integral is accumulation. So now we're going to accumulate all of that. So right now, so far, we've only had, and then that's just extra definition, extra understanding. So I don't need to put parentheses around here. But so now with the area of one stripe, we're going to be accumulating infinitely all of those many stripes from start to end. From the start to the end. Okay, so in the picture, think about the picture again. See, there has to be ultimately, and I brought this up earlier, but now if we put the stripes vertical, then starting end and ending has to be some values on the x-axis. So vertically, on the x-axis, at some value x equals a, that's where we start our stripes here, and we start accumulating it up to some ending x value on the x-axis. Okay, and so this ultimate ending from the left to the right, right? So this is an ending, and it's on the right according to this picture, from the left to the right, and this is an ending. This is the starts, okay, and this is the left end. It's just the way how we're looking at a graph in math at our level now. That's anytime we're looking at the graph, we're looking from the left to the right, and so that's fits perfectly with the concept that from the left to the right here, that left is our start and n is our right. And from there, we know that on the axis here, there has to be an interval where left n is some value being the beginning of where all of the accumulation is starting. And then all the accumulation is going to have to end at some x equals b value. Okay, and so in that way, now in the picture, see, start and end becomes from the left to the right. All right, and from the left to the right. And so now from that way on, this is the formula that's at the end of the day, in many standard textbooks, you're going to see right here. Upper curve is some f of x, lower curve is some g of x. We take the difference, f of x minus g of x. Okay, and then we multiply with the thickness dx. And then we're accumulating from A to B. And this is the formula that you will, at the end of the day, see being given in a lot of standard, in all of the standard calculus textbooks. But where did these formulas come from? As far as the area between curves, it comes from this fundamental. Okay, and then depending on how we chose our stripe, the orientation of our stripe. Currently, we're looking at vertical stripe. Okay, and so that's why thickness is dx, right? And the length here of the curve is f of x minus g of x. Okay, and right now we're completely looking at the picture. We based on the picture. Okay, and then when we later on get into some actual example, doing some actual examples, I will point out even more tips and hints so that you can identify your upper and lower curve even more effectively. Okay, so that's the situation where you're putting your stripes vertical. Okay, so back on my other board, and again roll back to that story, that imagination about a small child, very young child that attempting to color out a shape. Okay, so let me put away all of these extra drawing it because I only need the shape. We only need the shape. Okay. All right, so I apologize for taking some time to carefully erase, even though there's still some left over here on the board. Okay, but the same shape here. Okay, so there's a curve, and we want to find the area in between these curves here. So just think again about the action of a child who's a different child who's attempting to color this area. Then the child can also do this, or from the bottom up. Okay. For us now in these days, since we're a lot more mature, we're gonna go from bottom up right here. But children, they tend to go from top down. But now in the end, what I want to point out here is that the stripe in this case is in respect to the x and y axis. In reference to the x and y axis, then the stripe this time is horizontal. The stripe is horizontal. Any stripe is horizontal, up and down, up and down. Okay? And so in that way, any stripe has thickness. This fundamental will stay exactly the same. Any stripe has thickness, but I'm going to go ahead and erase all of these extra explanation here, because now we're using a completely different orientation of the stripe. So none of this is applicable to us. Only this original formula, only this original fundamental is here. Okay, and so like I said, any stripe. Now if I draw the stripe like that, horizontal stripe, it has the thickness. Okay, just like that, it has thickness, and then it has length, and that's why it has been already explained. Any stripe, it all depends on your pencil tip, and no matter how small your pencil tip is, your color pencil tip is, it's still going to give you a thickness. Okay, so that's why it's still just the thickness times the length that gives you the area of one stripe. and then we're accumulating from some start to some end like that. Okay, but now let's observe our picture a little more closely. Okay, so now I don't need too many stripes. I only need one stripe, and that's enough to tell the story. Okay, so the thickness of the stripe now is going to be measured in terms of a change, even though infinitesimally small change. And that change there, in the way how I need that to be, infinitesimally small, it has to be a change of value on the y-axis. And that's why the thickness now for a horizontal stripe becomes the dy. Okay, so now that formula of ours is starting to evolve. Thickness now evolve to become a dy instead. Okay, and then now we already have thickness. Now we need to find out how do we determine the length of our stripe, of any of our stripe at any instance. Okay, and so in the way how it is now, so back on the board. So now if we draw our stripes in this picture, if we draw our stripes horizontally, if the child is coloring with the horizontal stripes like this, then see, if the child is going all the way through like this, the teacher is going to come around again and trying to and correct the child, because this is too much, right? And this, if we're doing this, then we don't know where to stop. So the better one here is we're going to have to make the stripes to be anywhere restricted between. But look at the picture here, left curve and right curve, right? Because left and right this time define the length of our stripe horizontally. It's just the way how pictures are, how physical pictures and images are. Okay, and now mathematically, so this is the right curve. Okay, that's the right curve, and there's the left curve. Okay, instead of left end and right end, well, because it's the end of the two ends of a stripe like that. Okay, so left curve and right curve. All right, and so now the length of any stripe, and in the way how we already understood so well in math, further to the right means more positive, right? And more on the left means more negative, or lesser values like that. So that means to get the actual length between here, we have to go from the curve on the right hand side, subtract the curve on the left hand side, and in that way, further our formula becomes following. So the length now becomes the right curve, the difference between the right curve minus the left curve. Okay, that's how it is to get the length of any stripe, okay, at any instance. And so in just like how I explained earlier when we were still using vertical stripes, now since our stripes being horizontal, consequently it led to the d expression here has to be a dy. But now in that understanding we have had from earlier discussion about integral, then the d expression has to always be consistent with the main variable driving these curves right here. So that's why the right curve here, I have to express that as some function r. So r is for right. Many textbooks use e and f or whatever, but I go with the concept left and right. So r, but r of y. Okay. And this is L, left curve, f of y, L of y. Right curve as a function of y, left curve as a function of y. Why do we use y variable? Because these variables have to be consistent with the d expression we have already chosen for ourselves. Okay, and it all consequently came out as how we chose our stripe as starts. Okay, and then of course in some video, in some examples later, I am going to show the students how to effectively decide to use a vertical stripe or the horizontal stripe. But here it just, after we have already chosen the orientation of a stripe, it decides our d expression. That's the general. And then our d expression decides what kind of variable we need to express our functions in terms of. Okay? And so now with that, it's now accumulation. Because everything here before the accumulation is only the area of one stripe. And now we're going to accumulate from a start to an end. But start to end now, according to the way how the picture is, then we start from some low value of y. So how about y equals c here? And we're ending in the accumulation at some upper, okay, y equals d value. Okay, so start to end is now going to be on the y-axis right here, on the values of the y-axis. Okay, and so now it's from bottom, okay, to top. That's there for now, from bottom up, right? And so there, in that way, now, you know, at the end of the day, when you're reading it into any textbook, the textbook is going to start saying that, you know, if you use your stripes horizontally or to integrate in respect to y, then you have to write your integral, set up your integral as some r of y minus L of y, and then we're multiplying that with a dy, and then we're integrating with respect to c from c to d. But see, simply, if we're just simply staring at a formula like this, then it's not very useful to understand and it's going to be a very painful work to derive the setup right here. So stay with the fundamental understanding here so that it will get you into the proper setup of your integral, and then your integral will be finally the one giving you the proper calculation for the final answer. Okay, and so now at this point right here, after this point, I am going to start giving the examples about how we can find areas, and I will deliver the examples in the order from the simpler one to the more complicated one. Okay, and then so now again, back in what I was explaining, going with the vertical stripes or horizontal stripe completely depends on your decision. And so I am going to start out with a few examples first that I show you how to work after I have already decided the orientation of the stripes. And then at the end of each example, after getting the final answer for the area, I am going to, before closing down the example, I am going to explain a little further. I am going to give some additional clarifications of how it made me choose the stripes to be vertical or horizontal. And then as you have seen those examples enough, you're going to start drawing some good experience for yourself. Then there will be some examples after that to let viewers and users to follow and for you to be able to make your own decisions about how you can choose a dy or dx, or choose a vertical stripe to use or horizontal stripe to use. Okay? All right, so now we are ready to get into our examples for finding the area between curves. So allow me to now introduce example 1 right here. Okay, and so we're now at example 1, and so it is going to take a lot of writing on the board. So I have prepared the actual wording of the problem on my lecture note here, and so let's go ahead and turn over to my lecture note and have a look at. And I need viewers and students of mine to have a close look at every detail in the way how it's worded, so that there are a lot of things to learn as well in the way how each problem is being worded. All right, so here we are at our first example. Okay, so the question is asking us to sketch and find the area of the region bounded by the curves. So there's y equals e to the x, there's another curve y equals x, and there's a curve x equals 0 and x equals 1. Okay, so these are the curves here. And now, first of all, let me switch over to the graphing space right here, and let's quick, because the question did also ask for a sketch, so we want to sketch. Okay, and then after we sketch, because even if the teacher does not require, even if any teacher does not require the students to physically sketch the problem, but when it gets into this kind of problem, it's an unavoidable thing that we have to be able to see the picture. So at least have a sense about what the picture look like. So sketching is always the first step right there, so that you can see the picture, you can look at the picture and have a plan for yourself about how the problem works. Okay, and with this kind of application, with this kind of problem where we apply the definite integral, then it is highly recommended that you start working on your visual sense a little bit, so that you can start looking at picture. And sometimes if it has to, you can look at your paper and turn the picture around so that it's gonna work. Okay, so now, since the problem is saying sketch as a first step to find the area right there. So sketch is before finding the area. So now I'm going to turn over to the graphing area. Okay, so now on our graphing area. Now I use Desmos.com right here, but aside from this resource, there are a lot of other resources out there, including the famous, the quite popular standard TI-8384 calculator with graphing capability that can handle this. I decided to do this on my lecture here to use the Desmos because I like the resolution of the graphs a lot better, and the flexibility of Desmos.com right here. All right, and so now the idea now is we have one curve. So here's the graph for e to the x. So y equals e to the x is this graph right here. Okay, and then we got y equals x. So there's another graph. And then there's the line, there's another curve according to the problem that it says, let me once again swing back to the problem itself. It says y equals e to the x, y equals x, x equals 0, okay, and x equals 1. So let's look at these two remaining curves right here. So on my graph right here, x equals 1, x equals 0 is here, right at the y-axis, and x equals 1 is here. Okay, and so now we have 4 curves here being drawn. That's, I'm trying to, even though using the computer, I'm trying to make it I'm trying to pretend that if we are in that situation where we have to sketch, then just sketch all the graph. Just put a quick sketch, and the word sketch means we don't have to get the precise picture like how the computer has been giving us. Okay, just make a sketch, and then as long as we throw down on the paper all of the desired curves here, and then we're gonna start looking into the next description. Okay, and so now, according to the way how the lecture notes is indicating, then we want the graph. We sketch, and then sketch what? We sketch the region. The region is bounded. So now I want you to focus to this description right here. It's a region that's bounded by all of these 4 curves. So now on Desmos we draw the graphs for all these 4 curves. So now we want to sketch that region that's bounded by these 4 curves. So what does that mean by the region bounded by the 4 curves? Now, the term bounded by means it's something that completely contained. Bounded, it's the word. Okay, so we're looking at that region that's completely contained and being set boundary by all the 4 curves together. Okay, and that's the idea right there. And so now, in that understanding of ours right there, then if we're now looking at this, at the graph, then obviously it cannot be this region out here where my mouse cursor is currently pointing at, because this is only bounded, limited or set boundary by the y equals e to the x, and then the y-axis, but it has nothing to do with the other 2 curves. And this is only this area where my mouse cursor is only bounded by these 3 curves right here, not all 4 curves. And we can quickly check any areas here. So only the area inside here where my mouse cursor is now at. So let me quickly put a visualization of that sketch right there. So that area there. Now this area is the area that matches the description of the problem, in a sense that it is bounded between all, inside of all of these 4 curves together. Okay, and then x equals 0 is this vertical line, and then x equals 1 is this vertical line right there. All right, so now we're gonna have a clear picture of what the sketch and what the region is gonna look like. All right, so now with that picture, now I am going to, let me get back to the lecture note right here, and let's look at the next piece of description. So we want to find the area of the region bounded by the curves. But now, here is a very standard way of wording in any problem to find area between curves here. That's the problem will a lot of time ask you to decide. So you are the one who can decide this. So that's why the problem wants you to decide whether to integrate in respect to x or integrate in respect to y. Now, the wording here is a formal way of wording it, but what exactly does that mean by integrate in respect to x or integrate in respect to y? So I have explained earlier, just like how I explained in my general lecture, an integration is accumulation. An integration is accumulation. So integrate in respect to x means we want to set our integrating in respect to x means we want our thickness of the stripe is a dx. That's what integrating in respect to x means. And so that means, that also means the same as are we choosing to go with vertical stripes, or are we in that same region, are we going with horizontal stripe? Because horizontal stripes, so after what I have explained in a general the discussion earlier, then horizontal stripe will produce the y as the thickness right there. So this is, formally speaking, we're integrating, we're accumulating in respect to x, or are we accumulating the stripes in respect to y? That's what it is. Okay, so now once again, just for viewers and students of mine to get comfortable with the way how the problem is worded, that's how it says right there. But this is nothing but just how, I mean, we are left as our right here to decide which way we want to, which orientation we want to put our stripes. Okay, so this is only a simple example for now, and it's one of the first example where we formally apply the definite integral. So allow me to make that decision. Okay, allow me to be the one that makes that decision, and then at the end of the video, I will point out why I made the decision to go with one orientation of the stripe instead of the other. Okay, and then hopefully as we keep building up a few examples along that way where I will make the decision beforehand, and then follow along with that decision of mine in terms of the orientation of the stripe. And then after that, I will, viewers and students will start building your own experience in terms of how you can choose a good orientation of the stripe like that. Okay, so first example. So of course it's a lot of explanation for me to give, but then in the later examples I won't have to talk as much. Okay, all right. So now let's get back on decimals here. So in this problem, how I see it, with this area given right here, and with decimals, allow me to say that I am going to integrate in respect to x, meaning I am going to set my stripe vertically. I am going to use a vertical stripe for you. Okay, so here's how I see it. These are, pretend that this purple line right here is this purple line, vertical line right here is any stripe of mine. So as I move anywhere sideways from the left to the right, and you can see that as an animation here that the length of my stripe does change, and it varies differently depending on the instance where I'm at. Okay, but see, that's the idea of the accumulation. As I'm dragging my stripe further to the right hand side, and I have more area accumulated, and that's the idea right there. And so in this case, again, I have to admit that I have decided to go with the vertical stripe, meaning my stripe here is perpendicular with the x-axis and parallel with the y-axis. Okay, all right. So now in that way, let's see how things work right here. All right, so I'm going to leave the picture here for a little while. So And integration is accumulation. And so now in the way how I have already decided, and again, as I said, I will come back and explain why I decided to put the stripes vertically instead of horizontally. And so now we just need to remind ourselves. We need the length of the stripe, right, on each stripe right there, to multiply with the thickness. That's the fundamental that I want anyone to nail down right there. Any stripe has a length and has a thickness. The length is, the length is just the vertical height of that stripe here in this particular picture, and then the dx here is just the thickness. The thickness here in this case is going to be how thick your stripe is. Okay, and then that's multiplying that together. It's the area of one stripe. So now we're going to be accumulating from starts to the end right there. Okay, that's the fundamental that I want anyone to always nail that down before we really get into any problem of finding area. So now in the picture, in the way how you are currently seeing it, right, then I can also put another one right on board here, but the stripe is a vertical stripe. That means the thickness here, just like how I explained earlier in my lecture, in my general discussion, then this has to be a dx. Okay, so now we can take that information and start putting that in place right here. All right, so now just like that, here thickness becomes dx. Okay, and along this way here, my intention now is that I am showing viewers who are following along with this lesson, or students of mine who are following along with this lesson, to also be learning that skill, how you are able to set up your own integral out of this general fundamental. Okay, and so now we've got thickness, and remember, so now whatever we're setting up here, we got to set up the integral in a way that the function here has to have main variable x, because look at our thickness right here. Our thickness is the d expression that has x. It's dx. Okay, but now since our curve, since our stripe is standing up vertically like that, right? Then so it needs to be the height, and the height in our, according to our general discussion earlier, then it's going to be the upper curve subtract the lower curve. So let's see. So here we have the advantage of having the graph, seeing the graph right now, and the graph right here, the computer gave us the graph that's easy to recognize. So let me put away some of the fancy stuff here. Okay, let me hide away that thing. But between the two graphs right here, then this is e to the x, y equals e to the x, and this is y equals x right here. And so the graphs here is doing a good job in terms of telling us who's the upper curve and who's the lower curve, because you see, so now the height, the vertical height of any of our stripes right here is restricted or limited between upper curve and lower curve. So we just simply take that difference between upper curve and lower curve. That's how we get the height, the vertical height of our vertical stripe. Okay, and so vertical curve, but it needs to be in terms of x because of this. So in that reasoning, well, quick little scratch work right here to indicate, but well, it's never hurt to do. So upper curve, okay, and let me hide this away. So for upper curve, the function given there was y equals e to the x, and yes, it's already a function written explicitly in terms of x. So now I'm going to just go ahead and put it in upper curve as a function in terms of x. Why we want that in terms of x? Again, in that explanation that I gave earlier, because it needs to be consistent with this dx. Okay, and then what's the lower curve that we recognize? What's the lower curve that we recognized from the, and of course all of these extra thing I'm writing here is just extra steps to clarify for viewers and students of mine. If you are a student who study directly with me, I don't always require that you write this, but see, the more you write, the better documentation of your work that is. Okay, so never feel bad or never hesitate about how much details you have to write. Okay, so the lower curve in this case is, again, let's look at the graph right here. Right, so the graph we have right here, this straight line is obviously, according to the picture, is below the bent curve, and this straight line right here was the graph for y equals x. So in other words, now we have found the lower curve to be y equals x. See, the reason I have to specifically mention it clear and use the graph here to indicate, because you have to understand that the lecture note itself will never tell you. See, the lecture note only gave us 4 curves, but the lecture note will never tell. I mean, the problem, the description of the problem will never tell us, and will never tell any of us that among all of these curves, who's above, who's below, and all that. It's us who have to know the property of these graphs are here to decide. Okay, and so that's one way to understand. So now the lower curve is this function, and again, it's a function already expressed in terms of x, being consistent with this expression. So we're good to go. So now we have lower curve simply as a one function. It's x. So now I'm looking at upper curve minus lower curve according to how I explained in a general lecture right there. So now we have e to the x minus x. Okay, and so upper curve minus lower curve gives me the length of any stripe. So now when I'm looking at any stripe right here, okay, at any instance, the length of the stripe, the vertical height of the stripe is going to be just how much difference between the upper curve and the lower curve. Okay, and that is the reason why I was doing that subtraction between. All right, so now this is at one instance of x. We've got the area for one stripe. And so now an integral is accumulation. So now in order to achieve the area we need, I am going to accumulate all of these stripe areas, from the start to the end. Okay, and so think about what makes sense here. And I don't need to keep swinging back and forth on the graph, but now if we put vertical stripe, then we have to start on somewhere left and keep vertically accumulating from the left to the right, right? So start to end. So it makes sense again that it's going from the left to the right. And so now let's have a look at the picture again. In a way, how I'm doing this, then it looks like I start the region with a vertical stripe that align with the line x equals 0. Okay, and then as I keep progressing and as I keep moving toward the right hand side, toward the ending of our region, and you can see the change in the height, right? At every instance, the height of the vertical stripe here changes, and that's why we're accumulating it. And so and it looks like we're ending that when our x value hits right at x equals 1. So x equals 1 is right here. So now in that way, all right, so now in that way, it is apparently clear that the integral setup is from 0 to 1. So now we have a successfully set up integral. And this integral is simple enough for any one of us to start applying the fundamental theorem of calculus to evaluate the actual area and the actual amount of area. Okay, so now that area can be precisely found by doing that setup. And so fundamental theorem of calculus at this point says in order to evaluate this, we take the derivative of this main function here. And of course, once we set it up as a complete integral, a complete definite integral, then all of a sudden we realize this is a function. E to the x minus x is a function. Okay, and then we're integrating that function in respect to x variable. And so the fundamental theorem of calculus indicated for us that we can just simply take the antiderivative. So antiderivative on this first term of our function is an e to the x. Okay, antiderivative on this second term after the subtraction is simply a 1/2 x squared. Simple function on each term right here to take antiderivative. And then from there, at this point, we don't need to carry that symbol anymore. Okay, and then now we're evaluating from 0 to 1 according to the fundamental theorem of calculus. All right, and so now we can just simply substitute values in. So e to the first power minus 1/2 times 1 squared, that's the antiderivative evaluated at 1. And then I am going to subtract, okay, e to the 0 minus, maybe I didn't leave myself enough space here, so let me minus, and now e to the 0 minus 1/2 times 0 squared. All right, and so that is the setup calculation for this. And so now in the next step, and this problem here is adding into a calculation that's simple enough, so I can follow along. So here, all of that in the first pair of brackets is an e minus 1/2, okay? And then here e to the 0 is a 1, and then all of that here is 1/2 times 0 squared is a 0. So really we're subtracting just a 1 right here. And then minus 1/2 minus 1 are really like terms. I mean, they're not that, they're all constants already, they're all final value, but at least we can still combine numerically with these values. So in exact expression, we're looking at e minus a 3/2, and that is our total final answer. Okay, so now ladies and gentlemen, this is the final answer of our particular problem. It's the area, how big the area of this shaded area in our sketch right here. All right, so that's how big this area in blue. Okay, so I explained a little while ago when I first introduced the concept of definite integral as well as when we bring that into finding area. So let me recap that idea a little bit. But so this is the area, but the answer was an e minus 3/2. Now 3/2 numerically is a 1.5, e is about 2.7 something. So subtracting out, we're still having an area of about 1.2, something like that, 1.28. So 1.28, but 1.28 of what? Because keep in mind, the whole idea in calculus here is that we learn about the calculation, but we never pay much attention to units at all. So to e minus 3/2, what is the meaning of this, of these units right here? Or I have spelled it out earlier, it's about 1.28 as the total area. So what is that? What exactly is that 1.28 representing? It just means, now allow me to quickly put on the grid right here, okay? And then put on the grid's number. And so you can see that on my scaling right here, then 0 is here, 1 is here, so 1 unit square is about this big of area, 1 unit square on this graph, whatever graph that is, however long length we define, but 1 unit square. So this whole area is about 1.28 relatively compared to that 1 unit square. Okay, and that's the meaning of the final answer here. All right, so now, in this way, allow me to, so this problem was done, such a simple problem. It did not, and observe how I set it up. In the end, I set it up, it's only one integral. It's only one integral. And I mentioned that before we proceeded. I chose this, okay? So now it's time for me to explain why I chose that, because in the beginning, in the earlier part of the lecture here, when I was lecturing when I was giving that general description, that general discussion about the approach, and anyone doing this problem can have a choice between going with the vertical stripe to produce dx here, or going with a horizontal stripe to produce a dy. So how come I didn't go with the dy here? How come I didn't go with how come I chose not to go with the horizontal stripe? And instead I went with the vertical stripe right here. So let me quickly swing over to the other board, okay? And this time allow me, because in the end any computer is not as flexible as what we need. So now I have to quickly make a hand sketch right here, okay? So the e to the x is here. And forgive me to be a little bit off scale. Okay, and then the y equals x is here, and now of course we clearly know who's the upper curve and who's the lower curve. 0 is here, and 1 is here. Okay, just about there. So the area we're looking at is in here. Okay, and allow me to make the kind of slanted shading. So now what if I go with horizontal stripes? So let me use a red marker over here to indicate the idea here. Now here's the consequence of going with horizontal stripes. You see, we go from the horizontally, if we creating horizontal stripe, then we're going from the bottom up. Okay, so our stripes are going to be placed like this. So pay attention to a couple points right here. If I draw those lines being parallel to the x-axis, okay, that's this line right here. Pay attention to that line. Now, if I put any stripe below that red line right here, then our stripes is going to be, right curve is this line and left curve is this vertical y-axis. Okay, see, anywhere in here, anywhere below this big solid red line, then our stripe has length defined by the difference between the right curve is here, the left curve is here, the right curve is here, the left curve is here, the right curve. Okay, but now think about it. If we keep accumulating and go above that red line, okay, if we now go above that red line, then think about the impact right here. The stripe, the stripes go above this big red line right here as a breaking point. I see that as a breaking point. Then now right curve and left curve actually switch. Left curve still remain this straight line right here. Left curve is still remain this straight vertical line, but right curve is no longer this line. Right curve in this time is actually this straight line as x equals 1 right here, and x equals 0. So we have to definitely run into some situation about changing from one curve to another curve, just to work with the idea of right curve and left curve. So right curve itself already changed from this slanted line and switch over to that vertical line right there. Okay, and that's not all that is yet. And then I should have used a black color for these. Okay, so red line is to be the critical to indicate there's some breaking. There's changing in behavior of the horizontal stripe right here. Okay, so when we're above that red line, we know that right curve is no longer the same with this. Okay, and then there's another red line right here. There's another red line I have to draw. This red line right here, because here anywhere now, if we place a horizontal line above that red line, okay, if we place a horizontal line above that red line, this horizontal line will stop at the same right curve, but it has a different left curve here. Okay, and so it's a lot of breaking up and changing in the curves, either on the left side or on the right side. Okay, and so if we're doing it that way, then the way how I'm seeing it, we have to produce three separate integrals. One integral accumulating from the very bottom here, y equals 0 to about wherever that is here. Okay, wherever that is here. And then we can call that some y1 value, and this is some y2 value. So we have to produce an integral from 0 up to the y1 value, okay, of whatever the right curve in terms of L, in terms of y, minus the left curve in terms of y. And we have to, of course, rewrite all of these curves, re-express all of these curves in terms of the y variable, and so that the thickness can become a dy. So that setup right here, from 0 to y1, from 0 to y1, is only for all of that area accumulated by horizontal stripes from the bottom up to y1, right at this first red line. And then we need to accumulate with the area that's between these two red lines. And so that means we're going to have to produce a separate integral. Okay? And so now it goes from y1 to y2. Okay? And then it's going to have to be a different pairs. So how about here? I'm also going to have to call that, I can name that capital R of y, and then capital L of y right here. It's a different pair of right curve and left curve, and multiply with thickness dy. And that's not all right there. So all of this middle integral over here is that part. So you already saw that how much more efforts we need to if we decided to go this route right here. Okay, and then of course here it's just I don't intend to go that way, so that's why I'm only introducing the idea. And then there will be another example later where I'm gonna show you completely two different ways so that you can have a direct comparison between which way is effortless and which way is more effort. Okay, and then with this one right here, we still need another integral that we accumulate from wherever our y2 to the ending one, and the ending one is wherever that is here. Okay, the ending one is wherever that is here. I can call it y3. Okay, so y2 to y3, and then etc., and with thickness dy, and so much effort. And of course, how can I tell so quickly? First, well, it took me years to work on my my visual sense to look and decide. Okay, and so I want to pass that down on anyone viewing this video over here. You can also start learning to look at picture and observing picture. If you have to, now sadly I cannot physically hold on to my board and turn it around. If you can draw the picture on your paper, draw it around so that you can, even though you plan to go with horizontal stripe, but you can turn your paper around so that you can treat these as vertical so that you can see how the behavior of these curves changes. Okay, and so this is, I can see that I'm not saying that it cannot be done, but it's gonna take a lot more efforts compared to now in the situation we have right here. In the situation that we already have done. The shape right here, if I was going with vertical stripe, look at how convenient that is for us. At every instance of x, from the left to the right, from the start to the end, at every instance, we only encounter, at any instance, the height of the stripe can only need to be found by simply one upper curve the whole time, subtract one lower curve the whole time. We just never had to switch curves at all. Okay, and that's one of the biggest, and actually that is the biggest reason why why I chose to go with dx in this case. And that's also the big thing to always the biggest thing to watch out for anytime you're in that position to decide whether you're going to be integrating in respect to x or integrating in respect to y, or whether you're going to be using vertical stripe to produce dx or using horizontal stripe to produce dy. Okay, and so that's how it is for this kind of problem like that. All right. All right, and so now let's look at example 2 here in this particular lecture about finding area between curves here, so that we can keep building our experience. So now let's turn over to the lecture note I have prepared here so that we can see the description of the problem in Word. Okay, so now just like example 1 that you have seen, and here we're being asked to sketch the region. So unlike example 1 there where it was using the word bounded by, so here in this problem it's switched over to using a different word right here, enclosed by. So we want to sketch the region that is enclosed by the two parabolas. So here we don't have as many curves given as in example 1. Okay, so we have two parabolas here, y equals x squared and y equals 2x minus x squared here. Okay, so let's sketch that region. Okay, sketch the region enclosed by the two given parabolas here. Okay, so in that way now I am going to switch over to my graphing calculator. All right, so this is the picture of the two graphs together, and for this problem I have an intention for not mentioning which graph here is the graph for x squared and which graph is the graph for 2x minus x squared. I have a reason why I'm not mentioning that in this video lecture, because as we are working through this problem, I would like to point out another hint right here for us in case anyone is not so experienced with the graph itself, then we can still decide who's the curve on top and who's the curve at the bottom right here. Okay, so everything we see here is there's a curve, there's a parabola pointing down, and there's a parabola pointing up. But so the way how I see now, we're completely letting the machine to handle the graphs for us, and everything we do now is that we're gonna try to find that region being enclosed by the two graphs. So there's the two graphs right here, but enclosed again is another word that means being trapped inside. Okay, enclosed is another word that being trapped inside. So think about it. If I place my mouse cursor in this area, okay, in this area right here, then doesn't look like it means enclosed, because see the term enclosed here means it has to be inside. It kind of implies the meaning that being inside. So this area is not being trapped inside. It has boundary being defined by the two curves here, but in the end it's an area that keeps flowing unlimited to this angle here. As we going that way, then we don't see any limit to that. And then is this area the correct area? Yes, it's not the correct area yet, because even though it's still being set boundary by the two curves, but in the end the area here still has a leak. That's how a lot of time I used to see it. It has a way that the area can escape out unlimited out here, unrestricted out here. Okay, and now this area sure is not. This area out here sure is not. Now the area in here is matching perfectly with the description. Only two curves, but the two curves this time cross each other and create that region being completely contained inside, and that's why it's called enclosed. Okay, so now let me actually bring in the actual shading of that. So there we go. So that's the shading of the enclosed area. Okay, so further. Now, unlike example 1 where it was, there's still a starting and ending. See, if we're using vertical stripes, then it starts here and it there ends there. And I will talk about that later. Or if we're using horizontal stripes, then we're gonna put the horizontal stripes here, and it starts at the bottom and it ends up here. But so the only part that's unlike the earlier problem in example 1 is that ending and starting are not clearly given. And ending and starting here came out because the two curves, the two graphs, cross each other. Okay, you see the start and the end right here. Either way we're going in whichever direction that we're putting our stripe. Either we're putting our stripes horizontally or vertically. It ends at this tip. I mean, it starts at that tip and it ends at the other tip. Okay, and so in that way right here, now to be a little more clear about the starting and the ending, we have to actually set the two curves equal to each other and find out the x values where they cross. Okay, so once again, x value or y value where they cross. We got to find out where the two curves are crossing, y value or x value. It all depends on what we do. Okay, and so. And now and later I'm going to put all that information together. But now let's one more time look back, because after now we have sketched the region. Okay, and I have not explained which one between the two graphs there is the x square, and which one between the two curves there is the 2x minus x squared. But now let's look at this next description right here. Again, just like example 1, we are that person. We are that person when we're doing the problem in charge of deciding which way we're putting our stripe at. Are we putting our stripe vertically so that we are integrating in respect to x, or are we putting our stripes horizontally so that consequently we're integrating in respect to y? Okay, so that's a decision that we can make. But again, just like example 1 allowed me to make a decision, and then I will explain along with that decision of mine. I will explain how to set up the integral in that decision of mine, and then at the end I will explain why I did not choose the other way. Okay, and so now back in the picture itself right here, allow me to mention that I actually will go with vertical stripe. Okay, so now observe my vertical stripe. Think about if I place a vertical stripe anywhere and accumulating it from starts on the left and ending on the right here. Okay, then that's how my stripes look like. So my stripe again look as a purple vertical line right here. So again, as I said, this is a decision of mine, and I will explain the reason why I decide to go with the stripe later at the end of the video lesson. But here in this entire problem right here, let's approach the problem by accumulating areas of vertical stripes. Okay, and so in the way how it looks in the picture right now, then again with that fundamental, I need, so any stripe has length of the stripe, okay, and then we're multiplying that with the thickness, that's to get the area of one stripe, and then we will be accumulating the area of all stripes from the beginning, so from some start to the end right here. Okay, and so in this case right here, in the way how I'm putting my vertical stripes, okay, then the thickness here is clearly dx. Okay, so now we're gonna slowly putting things in place. So for my integral, it's gonna become thickness here is dx. So now I'm gonna find my way to find out the length. So in the way how it is, then the length has to be whoever the curve that's on top, because the picture is kind of look like this. Okay, so there's a curve on top and there's a curve at the bottom. Start is here and ending is here. Okay, and forgive me that I'm not exactly on scale, but that's not the point. The point is we recognize that the region itself, it has a start, okay, on the x-axis, and it has an end on the x-axis here, and we're going to need to find out those values, because these are the values that are not so given. It's not quite ready yet. So we have to find out the starting of our region, and our vertical stripe looks as follows. But see the upper curve and the lower curve. Yes, it's upper curve and lower curve, but how among the two curves here, x squared and then the 2x minus x squared. Okay, which one? And by the way, another check for consistency. Just like I said, we decided to go with vertical stripes, so consequently we're ending up with dx expression, with dx differential. And so that means whichever upper curve or lower curve, both of them need to be expressed in terms of the variable that's consistent with this. They already are. They already expressed in terms of x. So we're good to go with the variables here. Okay, but now, how do I know? So this is the part where allow me to introduce some solid work to always check, because we cannot always rely on graphing technology right there. Because even if we have pretty powerful graphing technology, there will be some graph that even with the super powerful graphing technology, you still won't be able to tell the who's above and who's below by simply looking. Okay, and that kind of problem will come sometimes. And so now, first of all, with this technique right here, allow me to hold on to this. Okay, because so there's the upper minus the lower. Right now we still a little bit undecided. Okay, we know that's what our plan is. We're undecided. I would say with a problem like this, where the two graphs are actually crossing each other like that, let's go ahead and find out first that where they are crossing in terms of the x value. So on the x-axis here, what's the a value at the start of the crossing, and what's the b value on the x-axis where it ends the crossing, where another crossing happens. Okay, and so with that work, then our two functions already in terms of x. So I'm going to go ahead and equate x squared with 2x minus x squared. All right, and so now 2x minus x squared equated with x squared. Here we can bring all the terms to the left-hand side and giving us 2x squared minus 2x equals 0. And then quickly we can see that this equation is a quadratic. You can have different options to solve that. It will give us two solutions. One of them is x equals 0, and the other one is x equals 1. And then how did I solve this so quickly? I leave that for viewers and students of mine to verify this, because as you arrive at this video lesson, you should have been doing a lot of algebra and fluent enough to the point that you can easily solve this equation. Okay, but so now among the two values here, 0 is lower than 1, so it makes sense now that on the x-axis here, x equals 0 is going to be the start of our of our regions. Okay, if we're looking from the left to the right, and again, the reason we're looking from the left to the right is because we are accumulating vertical stripes. So when we're accumulating vertical stripes, we're accumulating from the left to the right, start to end from the left to the right, and then the ending here is x equals 1. Okay, so I keep referring back to example 1 in a sense that example 1 had the start and the end trivially given, quite obviously given. But here we have to do some math to find the start and the end of our region, simply because there's this crossing nature. So the author of the problem didn't even bother mention. It's us who need to also be responsible to find these crossing points, and so that it defines our start and our ending of the sketching region right here. Okay, so now let me put away the picture. So now we know for sure that, I recall that we still have not finalized who's our upper function and who's our lower function. But now we know that the function, the upper function and the lower function, this difference right here must happen, or the accumulation must happen anywhere from 0 to 1. Start at 0 and ending the accumulation at 1. Okay, and so now here's how we can decide who's the upper function and who's the lower function. See, there are two functions. One of them is f of x equals x squared. There's a g of x equals 2x minus x squared. Like I said, the graph did not tell me the story, because think about, I can pretend that I can be that person who is not so experienced with graphs. There are students who arrive at calculus but still not so much a big fan of graph. Okay, so in that case, if you're not so much of a big fan of graph, of viewing graphs, or if you're still a little bit shaky with the properties of graphs, and these properties don't come back immediately, then there's always a way to check. Now you know that your regions, all you need to decide is in between this interval from 0 to 1, who's above, who's below. Okay, we don't need to worry about, hey, who's above and who's below before x equals 0 or after x equals 0. We only need to decide who's above and who's below inside of that interval from 0 to 1. That's another important point to understand, to be addressed. So in that way, now we have a good, perfect way to narrow down right here. Pick a value randomly, because now we know that we're only turning our attention within this interval on the x-axis from 0 to 1. Then pick a 1/2, like some value. Doesn't have to always be 1/2, 3/4, whatever that's the comfortable for your calculation. But pick a 1/2. Pick a value inside of that interval. And now I'm going to substitute that value into both functions here. Whoever gives the higher value, that has to be the upper one. It's that simple trick. Okay, it's that simple hint right there, but it works anywhere. It works anywhere in case looking at the graph doesn't tell the story. Okay, and now I don't have a calculator immediately with me here, but f of 1/2 here is a 1/2 all square. So that gives me a positive 1/4 or a 0.25 in case anyone so loves you working with the numerical values. And then g of 1/2 is 2 times a 1/2, which is a 1, and then minus a 1/2 all square. Okay, so see, 2 times a 1/2 is a 1, but minus 1/4. So this actually gives me a 3/4. So now we have, or a 0.75. So now you have a clear answer between. So now we picked a random value in between this interval, and we found out that, hey, so in the conclusion now, inside of this interval from 0 to 1, this function g right here. See, it doesn't always have to be g is the lower one. And see, the dangerous thing with reading textbook, if once this textbook set out a formula, then people tend to just memorize that textbook without much realization about it. But the idea now is that who's the upper one and who's the lower one. So after we made judgment here, then the upper one in this case is the 2x minus x squared. That's our upper one. And the x squared is the lower one. Okay? And so now, and that's the way how we are deciding. So now in that way, I can put away all of this scratch work right there. All right, so here we go. And I just now realized I need a lot more space, so I am going to erase my partly done integral setup, but move that integral sign a little further. So now in brackets right here, so there's still that dx multiplication there. All right, so that's the thickness. Now we need to produce the proper stripe height right here. So upper curve this time is the 2x minus x squared. Okay, and then lower curve is simply the x squared. So there's my upper curve, lower curve. Now our integral is completely set up. Okay, so it took me some time to explain, but think about it. Once you are fluent with this, it's not that hard at all, and it should move on pretty quickly. It should be done pretty quickly. And so now the good news is that, see, throughout the entire region, so in this way how I'm setting it up, throughout the entire region, there's only one integral to work with. We don't have to break it up into multiple integrals and then add them the results together. Okay, so now at this point, our integral is finalized as an overall integral from 0 to 1, and then just do a little algebra on these terms here. It's now a 2x minus 2x squared. That's the stripe height determined by the value of x at any instance. And then we multiply the stripe height with the thickness dx, because it's vertical stripe again. And then we're accumulating all of those stripes areas from 0 to 1, starting at 0 and ending the accumulation at 1. And so now just strictly just follow that straight fundamental theorem of calculus here. We're looking at, now first term gives me, in terms of the antiderivative, it's just x squared. The next term here gives me a 2/3 x cubed. All right, and so now at this point we are ready for evaluating from 0 to 1. Okay, and so 1 substituted into each term here, we're looking at 1r squared, or maybe let me write it in the next line right here. Okay, so 1r squared minus 2/3 times 1r cubed. This is the antiderivative at x equals 1, and we're going to subtract again. And believe me, experience will tell you immediately. But now, since allow me to assume that there are still beginners looking at this, so I am going to carefully substitute this value into each term. This value 0 into each term of our current antiderivative here. So 0 squared minus 2/3 times 0 cubed. But now anyone can see that this will quickly become a 0. And so all we have now is final answer will be, I'm running a little bit out of space here. So the area, see, so much explanation, but the work, once we set it up, it can be just done in one little short space of my little board here. So the final area here is going to be, so that's 1 minus 2/3. Okay, so that's going to be 1/3. That's how big this area is. Okay, so let's look at the graph again. 1/3, it's the area being 1/3. 1/3 of what? So alongside with how I have explained in some of the earlier video lessons about the meaning of these areas we have found. Okay, then so on the graph here, see, once we completed that area, okay, once we have completed that area, then 1/3 of what? So now allow me to bring up again the grid, okay, and some of the axes value right here. So this unit square right here has area 1. So 1 unit square. So the area inside being shaded in blue here is about 1/3 of 1 unit square. So everything, every area value that we finally calculated, it's being measured in terms of relatively to the number of unit squares, to how many unit squares that is. Okay, so now that we're done with this problem, nice and easy, and we've learned a little bit of the math work to find out, and that will become our responsibility quite often out there when we're working with these problems. A lot of times the curves, they're crossing each other, so it is our responsibility to find where the curves cross. And there could be even more than one places where the curves cross. So know how to solve these equations algebraically. Just simply set one equation equal to another one. Okay, and then another experience I want to add on to point out in this problem here is that so just like how I explained earlier, see, after we found the starting point and the ending point and we set ourselves, we narrow our attention. Of course, this is after we made that decision that we're using vertical stripes. And then now we know that this is the beginning, the start of our accumulation of all those vertical stripes, and this is the end right here. And so as we're accumulating those from the left end or to the right end, we restrict our interval. We learn that little tip and hints that for graphs that looks like that, and after we already found out the start and the end right here, generally, then we can just simply pick a value somewhere inside of that interval window that we're trying to find the area of the region here, so that we can substitute that into one curve and substitute that into the other curve, and then find out to decide who's the upper curve and who's the lower curve, so that we can successfully set up our who's the upper curve and subtract the lower curve in the context where we already decided that we are accumulating with vertical stripes. Okay, so that's another experience I want to add on. So now the last explanation I want to give about this problem. So just like that, the problem actually from the beginning left that decision for us to decide whether we're using vertical stripe or horizontal stripes. So I decided, I mentioned in the beginning of the example here, I decided to go with the vertical stripe so that it consequently produced a dx here and gave us all this here. So why did I do that? Why did I do that? I just want to share a little bit of experience of mine right here. So in terms of why I chose that. Well, in this case right here, or maybe let me draw a hand sketch version on my other board that would be looking better. All right, so now think about this. So we have one curve going this way and the other curve going the other way. Okay, so as far as so we chose vertical stripes. Okay, and that worked, and it was pretty simple. So now it's all about the amount of effort. So what if we chose a horizontal stripe in this case? So if we chose horizontal stripes, okay, then the stripe looked like this. Now, in this problem, if we chose the horizontal stripe, then it's not as bad. It's not as effort costly as example 1, because we don't have to. It's still one same curve being on the right hand side, and it's still one same curve being on the left hand side, no matter where you place your horizontal stripe. Okay, pause the video, have a moment to understand what I just said, try to digest what I just said. No matter in this particular picture right here, in the way how the region is set up, unlike example 1 that I delivered earlier, no matter where you place your horizontal stripe, it won't be as bad in terms of effort. It won't cost that much more effort. Okay, because it's, I mean, as far as I see, we can still, doesn't matter where we put the stripe, the horizontal stripe, it's still got just one right hand side curve, subtract the left hand side curve here. So it's not going to be, we don't have to face that difficulty about, the curve itself on the right hand side changing depending on different zones where we put the horizontal stripe. So we don't have that kind of problem. But it's still actually a little more effort here compared with going in the direction where I chose a vertical stripe. What's the little extra effort we have to do here? The curve itself, in the problem, the curve itself was given in terms of x already. The curve itself, both of the curves itself was already in terms of x. Okay, so basically I still want viewers and students of mine to keep in mind that going with dx or dy is on your choice. We can decide that. But then any decision has a consequence. So now if the curve, it's just the problem, the author of the problem who gave us, he or she, whoever gave us the problem already gave us the two curves expressed in terms of x. Okay, so after I decide to go with vertical stripes, then I had dx that leads to vertical stripe having thickness dx. Doing that, I did not have to rewrite these expressions in terms of y. I didn't have to re-express this. But now the consequence here is, what if we go with the stripe, with this stripe right here, the stripe being horizontal, then the thickness now is going to be a dy. That means the first curve here you have to rewrite. So y equals x squared, you have to rewrite algebraically. That means positive square root minus of y to equals x. And that means you have to choose the proper one, the correct one, because plus and minus square root are actually two different functions, two different curves here. Okay, so we have to rewrite that and choose the proper one. It's already a lot more effort. And then this one here you also need to rewrite. So you need to solve for x as a function of as some function of y right here, and it will take some more time as well. And so if we are going with the horizontal stripes, as far as the picture, we don't have to worry about the stripe. We don't have to worry about the left and right curve changing behavior, but we do have to face with that problem about rewriting each of our curve in terms of the opposite variable right there, where it's right here in the problem it's already in terms of x, so it's more consistent with that decision I made earlier about going with a vertical stripe. Okay, and so that's the reason why I chose to go with dx, with the vertical stripe in this case. So in any way, up to this point right here, we've had two examples, and the whole idea now is that deciding to go with a vertical stripe or a horizontal stripe, one way will always produce, will a lot of times produce more efforts than the other way. And so in that case, in that reason, and of course, the more you spend time to work on these problems, your mind will become more focused and get sharper in terms of looking at the picture and be able to tell immediately. So it's not going to take so much work to decide, okay? And your natural sense will start kicking in someday, okay? But then once we can see that one way of using the stripes will cost more efforts, then we're gonna stay with the decision that's easier, less efforts for us. Okay, so this thing right here, we only have one integral set up. We don't have to worry about breaking it up into multiple integrals, and it's already quite ready. Every curve given in the problem was already in terms of the variable that's consistent with our thickness of the stripe right there. Okay.